In today's lesson, we are going to be looking at function notation. Now, we've already looked at what a function is, and we've looked at how to describe functions and relations in that sense using domain and range. Now what we're going to look at is just different ways to write things. Right, so function notation is just a different way to write equations. You may have seen stuff like this in the past already, but it's not really going to change how we deal with them. It's just a different way to write. So for example, the shape of the Humber pedestrian bridge in Toronto can be approximated by the equation h of x is equal to negative 1 over 144x squared plus 5 over 6x. H is the height in meters above the water, and x is the distance you have to walk from one end as you cross it in meters. In total, the bridge is 139 meters long. This equation has been written using function notation. So take a look at this equation and see if there's something unique about this equation that maybe is a little different from how you've seen equations in the past, because this is written as in function notation. So is there anything different that you may notice about this? If not, that's okay. But function notation is most commonly seen as f of x. We see here f and then an x in brackets. You may also pronounce it as f of x, or another way you might say f at x. So different ways you might pronounce it, but all it is, or all it means, is that this f at x or f of x represents the value of the dependent variable for a given value of the independent variable. So all that's saying, just a fancy way of saying, the value or the y value for a given x value. So that's just a fancy way of saying the y value for a given x value. So in that sense, y and f of x can be interchanged. We can switch them in and out. We can also then use x and f at x to represent the solution for f at x. Basically saying the point x, y will be the same thing as the solution. So if we go back to that last example, instead of writing it as h of x, I could write it as y is equal to negative 1 over 144 x squared plus 5 over 6x. I could write that the same way, right? It's the same thing if I just replace h of x. Now usually it's f at x, you're talking about a function, but it might be different letters or variables depending on what our question is talking about. So as long as it has this general form, f at x, h at x, so on, that's function notation. So let's use this function notation to determine the height of the bridge as it crosses, or the height of the bridge above the water as it crosses the Humber. And we're told, or we know that the bridge is 139 meters long. So what we're going to do is we're going to look at the height for different values. So we're going to start at 0 meters. Basically, if we start at the beginning, we've crossed at 0 meters. We start at 0, and let's look at intervals by 20 meters, just as an example. Right? So that means we're going to create a table of values, x, and instead of y, we're going to write h at x. So the value when x is 0, when x is 20, when x is 40, 60, 80, and so on, just as an example. How do we find those values now? Well, now what we can do is we can substitute. Because what this means, if I have h at x, but I know that x is 0, I can write h at 0 is equal to, and in that equation, anywhere I see an x, I'm going to replace it with 0. So all that value is telling us is that I'm solving the equation when x is 0. In this case, it works out. So I substitute, then I'm going to evaluate, and then I get h at 0 is equal to 0. Because anything times 0 added together works out to 0. We can go through and do the same thing for a different example. Let's do h at x is equal to, or no, sorry, not h at x, we're going to say h at 20 is equal to negative 1 over 144 times 20 squared plus 5 over 6 times 20. And go through and solve, and I find that it's 13.89. And I can go through and do the same thing for all of these different values. Right? For 40, it'd be h at 40. 60, h at 60, h at 80, h at 100, h at 120, and so on. Right? We plug those values in, we start to get specific values. Again, you can go through and calculate these on your own if you want. But just for an example, we filled out the rest. And we did 2 of them anyways. So that's how you use function notation. Not really different from what we've done before, just different notation to give us a better idea maybe of what we're plugging in or what our final answer actually means. So again, when given a function f at x and asked to evaluate something, say for example f at 4, we substitute 4 into the equation for x. And this value here is telling us that we need to substitute 4 in. Or basically, in other words, find the value of y when x equals 4. So I have my given function. I have f at x equals 1. So here what I'm going to do, I'm going to show the substitution. So 2 times 1 squared plus 5 times 1 plus 1. We get 2 plus 5 plus 1. This gives us a value of 8. So f at 1 is equal to 8. For b, same idea, except now we have fractions. So 1 over 2 squared plus 5 times a half plus 1. And again, we can go through and solve this. So 2 times 0.5 squared is a half. 5 times a half is 0.25. And plus 1, we end up with 4. So that means that f at a half is 4. Again, we can go through some other examples. C, same idea. Everywhere I see an x, I'm going to replace it with 5. So I get 2 times 25, which is 50, plus 25 is 75, plus 1 is 76. So again, these should be kind of straightforward calculations. If you need to take an extra step to go through, that's fine as well. For D, what we have to do now, because it's f at 3 minus f at 2, we want to solve each one individually first. Solve individually. Oops. And then subtract. So we're going to solve each one individually first and then subtract. So in this case, 2 times 3 squared plus 5 times 3 plus 1 minus 2 times 2 squared plus 5 times 2 plus 1 should end up with 34 minus 19, which gives us 15. So again, we can go through different steps like that, where we might have to solve a function for one value, solve it for another value, and then subtract. So different scenarios that come up. we're going to look through a couple of examples. So the relationship between the selling price of a sleeping bag, S dollars, and the revenue at that selling price, R of S, or R at S, is represented by the function R at S is equal to negative 10 S squared plus 1500 S. So we want to determine the revenue when the sleeping bag costs $55. So this portion here, the sleeping bag, $55, this is actually S is equal to 55, right? The selling price. The selling price is $55. What would the revenue be? Well, we have a function, R at S, so I can replace the S with 55 because that's the selling price I'm using this equation for. And in my equation, everywhere I see an S, I'm going to replace it with 55. So negative 10 times 55 squared plus 1,500 times 55. This works out to 52,250. So that's the revenue when the selling price is 55. For B, we want to determine and explain the meaning of R at 85. Well, this value here, or this sentence here, R at 85, this is telling us, or this will tell us, the revenue when the selling price is $85. So that's what R at 85 means. Now to determine that, we have our equation, R at 85, our function. We plug in our value, our X value of 85, into our equation. And we go through and solve. And we should find that at R at 85, our revenue is 55,250. One final example for this question, or one final question, explain the meaning of 60 54,000. So a point 60 54,000. So what this is telling us two parts. The first part, the X value, is telling us the selling cost. The second part, right, that was S. So the selling cost. The second part is R of S, which is the revenue at the selling cost. So in this example, we can say the revenue is $54,000 when it costs $60, or $60, say, per bag. So hopefully we see that this function notation isn't really changing much. It's just a different way to represent things. Maybe it makes it a little bit easier when we're trying to represent, or when we're looking at an equation and seeing what we're actually doing, or maybe it's just easier to write R instead for some of you. But again, it is kind of a useful tool just to kind of shorten things or make it a little bit easier. So next example, the CIBC Everyday Plus checking account is $4 per month. With this, you get 25 free transactions and are charged $1.25 per transaction above 12. So basically, you get 12 free charges. The monthly charge can be modeled using the function C at t is equal to 1.25 times t minus 12 plus 4, where t is the number of transactions used per month. So we want to determine the monthly charge when you make 35 transactions. So again, the 35 transactions is just another way of saying that t equals 35. So what we want to do now is we want to figure, well, C at 35. What is the monthly charge at 35 transactions? I have my equation. Everywhere I see a t, I'm entering in 35. So 35 minus 12 plus 4. So 1.25 times 35 minus 12 plus 4, we get 32.75. So basically meaning that after 35 transactions, it's going to cost us $32.75. For B, determine and explain the meaning of C at 26. Well, this here is basically a filled in version of C at T. So this is basically going to tell us the cost, or sorry, not the cost, the monthly, well, the cost, the monthly cost, monthly charge for 26 transactions. So we've used this account, we've done 26 transactions. What is the monthly charge? So C at 26 is equal to 1.25 times 26 minus 12 plus 4. And again, we go through, make this calculation. Remember to follow BEDMAS, do your brackets first, then multiply, and then add. We get 21.5. So that means the monthly charge for using 26, we're going through 26 transactions, would be $21.50. Lastly, explain the meaning of 45 and 45.25. Well, again, we could break this down. This is T, this is C at T. What do those values mean? Well, 45 is the number of transactions. For T, C at T is the cost or the monthly charge. So this would say that the monthly charge for 45 transactions is $45.25. So that is the cost or the monthly charge that we would have to go through. So we've looked at some word problems, we've looked at some actual equations. Let's look at a graph. So this graph shows the function f. And we want to find the values when f at -2, f at 2, f at 70 for this function. Well, so how does this work? How does it work when we have a graph? Well, again, remember, f at x is basically the same as y. So this is basically saying at a given x value, which we see here, at a given x value, what is the y value? Well, let's go to -2. So we go over x is -2. If we go up, we see that the function, or our line, is 2. What about f at 2? So again, 2 is the x value. We go over to 2. Ooh, we see a couple things here. Hopefully we remember from the previous lesson, when we have a filled in circle, you'd say the value exists, or the function exists at that point. No circle or an empty circle, that point does not exist in this function. So that means that for f at 2, the value, or the y value in this case, is 2. F at 70, this one's maybe a little tricky because we don't see 70 on the x-axis. It's somewhere off to the side over here. We don't see it anywhere over there. But luckily, because we see this arrow, it means it's going on forever. This line is not going to change. So that means that all the way over at 70, we're still going to have a point here, and the y value is 1. So that means that f at 70 would be 1. Let's put some dots in there. Final question, find the value of x such that f at x equals 3. Or in other words, when y equals 3, what is the x value? So let's go over to our function. We find y equals 3. Let's see what values we have. Oh, well, looking at it, I can see that there is 1 point at y equals 3. In this case, our x value then is -3. So we could write this and say f at -3 is equal to 3. So this function equals 3 when the x value is -3, which we see from our graph. So when we have a graph of a function or a relationship and we're asked to find these values using function notation, it is very straightforward because you're just kind of looking for the y value at a given x value. So again, the main thing from this note is just understanding function notation, how it works. It is essentially very similar to what we've done in the past 2 years in grade 9 and 10, just written a little differently. So it might tidy things up a little bit or give us a little bit more information when we're going through and solving.